name is Adrian.
My name is Jackson.
I'm Matthew.
I'm Harry, and I'm down behind the camera. We're group B08. This is our project.
The reflow oven controller project calls for the design of a circuit and finite state machine that can autonomously facilitate the process of reflow soldering using the toaster ovens provided in the lab. Our team made use of our ELEC 291 individual kit and the Project 1 kit, along with equipment in the lab to construct this project. Our team was tasked to make an oven controller that could respond to temperature, stimuli, and timing cues. These cues would signal our state machine to change states, and thus change the intensity of the oven. The intensity of the oven is to be controlled by pulse width modulation. Our team began with a structured engineering approach to ensure each subsystem was reliably tested and validated before moving on to subsequent phases of the project. First, we focused on the hardware. We designed, assembled, and tested the key components, such as the operational amplifier, microcontroller, and user interface button, to confirm they function correctly. By establishing a stable hardware baseline, we minimized the risk of falsely attributing errors during software development to hardware issues. Our hardware design handles key aspects of this project: temperature sensing, power control, and providing data to the user in real time. The LM335 temperature sensor provides a reference temperature reading to offset and calibrate the thermocouple measurement. The K-type thermocouple generates a very small voltage difference when subjected to heat. The voltage is proportional to temperature. The op-amp OP067 amplifies the thermocouple voltage to match the microcontroller's ADC input range. For voltage reference and power supply, we use the LMC7660 voltage regulator. It provides a stable 5-volt voltage supply required to properly operate the op-amp, while the LM4040 provides the reference voltage for the LM335 sensor that is used to measure ambient temperature. At the heart of our hardware system is the microcontroller unit. The Nuvatron N76E003 microcontroller handles user input, controlling the oven's heating cycle via PWM and processing temperature data received from the thermocouple op-amp setup. The solid-state relay enables the microcontroller to control the oven by allowing efficient switching of high-power loads. The NFET and the diode protect against voltage spikes and allow for smooth SSR operation. Our hardware included 5 push buttons that allow the user to set and change the parameters of the reflow process and to start and stop the process. Lastly, there was a speaker that produces an audio cue for each state transition. The software aspect of this project is programmed using assembly and centered around the logic structure of a finite state machine. This logic structure is used to manage different stages of the reflow process based on preset parameters. In turn, the microcontroller will process temperature, data, updates the display, and responds to the user's input. Challenges and improvements. During our project, we ran into many issues with our code and hardware. As we were programming the interface buttons, a problem arose where our buttons could not make a selection for which of the 4 values to edit. This problem was eventually resolved. We encountered various other challenges while programming the finite state machine. The persisting issue we had before was the reluctance of the FSM to change her state. The resolution of this issue, unfortunately, was not done in time to give us a working FSM during our lab demo. The issue turned out to be we were confusing clear and set bit in our state flag commands. An improvement we tried to make to the reflow oven was a musical speaker. We modified the wait 1ms and the wait ms function to play a sound on the buzzer. The song played by the musical speaker was designed to only use timer 0 and done without an interrupt, as the interrupt for timer 0 was occupied by call speaker function, which played 1 beep tone. While we were able to program a melody with these functions, The one-timer design was difficult to integrate into our FSM as it caused all other processes to be halted for the duration of the song. To conclude this video, although our oven controller had trouble performing the state changes under the prescribed conditions, this problem was eventually fixed and all group members were able to have their own soldered EFM8 microcontroller. We learned many valuable lessons in technical development and team management throughout the course of this project. Thank you for listening to our presentation.